Probably the most challenging environment to manage human waste is the alpine environment. The alpine and probably the polar regions as well. It's very cold, very harsh environment. Freezing temperatures, 9, 10, 11 months of the year. You put together a sewage barrel in January or February and there's still a chunk of ice in it at the end of July. So trying to get thermophilic composting happening is not going to happen. It's sometimes, well, there's no soil cover. No soil covers, so pit toilet, just don't think about it. And some locations don't even see the sun for a few weeks in the winter because the sun is so low in the sky and the mountains are in the way. So trying to heat up the system by using a solar panel isn't going to work either. And yet this is the kind of environment that the Alpine Club of Canada operates. So BEES is a nonprofit collaborative initiative formed to facilitate research and find solutions for energy, potable water, gray water, which is kitchen waste, and black water, which is human waste, in off-grid alpine and subalpine environments. BEES doesn't actually do much research itself. It mostly chooses projects and tries to get the funders and the researchers together. So this project, Backcountry Blackwater Management Options Analysis, was commissioned by BEES, and it was undertaken by Stantec and SD Consulting Group. The goal of this project was to evaluate blackwater management options at remote alpine and subalpine huts in Canada's mountain regions in terms of life cycle costs and environmental impacts. So the information is intended to help operators of backcountry facilities choose the best option for their site. The options that we analyzed included the pit toilet, which is basically a hole in the ground and the microorganisms in the soil break down the waste. The barrel flyout system, where the waste is captured in barrels and are flown out by helicopter. Incinerating toilet, where the waste is burned on site. Carry-out system, where users collect their own waste and carry it out. And the heated chamber composting toilet. Two versions, alpine and subalpine, both similar with respect that they use urine separation, composting of the solids, and the remaining waste is flown out. But they differ in that the alpine composting system involves collection of urine and dehydration as much as possible before it's flown out, with an overall projected estimate of an 80% reduction in mass. And the subalpine system, the urine is actually treated and left on site because, well, in areas that have sufficient soil cover, with an overall reduction in mass to be about 90%. Neither of these systems actually exist yet, but this is research that we are looking into and wanted to be able to compare them with the other options that are out there. The analysis was on costs, so construction costs, operation and maintenance, total life cycle costs, and the environmental impacts were subdivided into user health, water quality, non-renewable energy use, and aesthetics. And they were rated on a scale of 0 to 5, 0 being no environmental impact, and 5 being a high environmental impact. And because solutions at any given location are site-specific, we provided the researchers with 3 real-life locations to do their calculations, and these are all Alpine Club of Canada sites. The first one is the Great Cairn Ben Ferris hut, which is a typical low-use alpine shelter. It's located in the Selkirk Range, near Mount Sir Sandford, an 11,500 footer. So in Canada, alpine refers to the area that is above tree level, which happens at about 7,000 or 8,000 feet. The Great Cairn Hut is a small hut at about 12 feet by 17 feet, and it sleeps 6. It's built right on the bedrock. When it was built in 1964, the Haworth and Silvertip glaciers would have been considerably closer to the hut. So this is actually recently deglaciated landscape, and the alpine grasses and flowers and small shrubs are just starting to take hold. The outhouse is a small structure, and for the last 20 years it has been a barrel flyout system, as with most Alpine Club of Canada huts. But within the last year, the Alpine Club of Canada is in the transition of changing this over to a user carry-out system. The second location, the Bow Hut, is a typical high-use alpine hut. In fact, it is the Alpine Club of Canada's busiest hut. It's located near the Wapta ice fields at an elevation of 7,700 feet, with the hut there, and its proximity to the Wapta ice fields. Definitely an alpine environment above tree line, very little soil cover. The toilet is actually connected to the building. We've got 2 of them here, with the barrel storage area out back and the flight deck. And an interior shot of one of the toilets. The third location is Elizabeth Parker Hut, a typical subalpine hut, gets moderate use. It's located near Lake O'Hara at an elevation 6,700 feet. Gets about 800 overnights per year. The Elizabeth Parker Hut and the nearby Wawaxie Cabin are built on subalpine meadows. I think it was built around 1919. Just beyond the trees there is Lake O'Hara, and this mountain here is Mount Victoria. So on the other side of Mount Victoria is the very famous and much photographed Lake Louise. The outhouse at Elizabeth Parker Hut is a double-seater with barrel storage in the back that go underneath here. And there's a wood storage area as well, because it is heated by wood. And just some typical barrels sitting under the chutes. And incidentally, these white strips on the floor here, the material is called puckboard or arena board. It's what you find in ice rinks. And we put it down there because it makes the barrels easier to slide. So it makes it easier for users to move out a full barrel and move a fresh one underneath. First of all, the alpine low-use location, typified by the Great Cairn Hut, comparing barrel flyout, incinerating, carry-out, and composting. We didn't include the pit toilet because it's just not feasible on the alpine. So if you look at construction, cost is the yellow, red is operation maintenance, and green is life cycle cost. The least expensive method at this location is actually the carry-out. And this is why the Alpine Club of Canada is switching from barrel flyout to carry-out. And then if we look at the Bow Hut, which is a high-use alpine hut, all of a sudden the carry-out is most expensive because we included the cost of the bags, right? And composting actually looks like the best option here. And at Elizabeth Parker Hut, comparing pit toilet, barrel flyout, incinerating, carry-out, and composting. Pit toilet is the least expensive, but I happen to know that the water table at this location is just too high, so pit toilet is really not a feasible option, which makes carry-out and composting the least expensive options at this location. This slide, the water table location, so pit really not option. Carry-out, posting. Least expensive. Incinerated at this location. Incinerated. Slide. The water table. Location. Incinerated too high. Incinerated. So pit incinerated really not an option. Carry-out, posting. Least expensive at this location. slide water table location. So pit is really not an option. Carry out which is hosting. Cat which is expensive. I use of this location. Which is cat which is I use slide cat the water table and location high. And so pit post and really not an option. And carry out hosting and expensive and at this location. And mountain is Victoria slide so a item of the water table location high pit best option really so not and really not ninth option carry out ninth hosting ninth most expensive ninth at this location ninth slide hut and water table hut and location hut and high hut and so pit hut and really not hut and option hut and carry out hut and hosting hut and most expensive at this location slide water table location high pit really not barrel flyout and incinerating are generally more costly than other options. Carry-out works best in locations that receive low use, but becomes increasingly expensive in locations that receive high use. Composting toilets cost less and have fewer environmental impacts than barrel flyout or incineration and are viable options in most locations. And there is not one perfect black water management solution for every location. There is just a selection of technologies to choose from. So the outcome of this project has led bees into further research into the composting process, urine separation and treatment, and a combination system of dehydrating the solids and incinerating them. Bees is very fortunate to have Geoff Hill here doing some research in the lab and on site, and he's looking into the composting process, and I'm actually going to bring him up here after I'm through with these few slides here. And bees is also interested in urine separation. Urine is actually a fairly friendly material. It is considered sterile. It doesn't contain the harmful bacteria that poo does. And there's less odor when urine and poo are separated than when they are allowed to mix. And we just calculated 95% actually of sewage is urine. So if we were able to separate the urine before it is allowed to contact the poo, we essentially reduce the amount of mass that you have to treat by about 95%. And there are toilet seats that you can get to do that. And these are being used not only in third world countries, but in Europe, in cities and towns in Europe, because they're collecting the urine and using that as fertilizer on farmers' fields. So this is actually our future. And in our urine separating future, even men can sit down to pee. And even women can contribute to urine separation. So ecological sanitation is about separating the urine and the poo and returning them back to the environment where they should go to fertilize the environment, increase the fertility of the soil, at the same time protecting the ground and surface water. So Geoff is also doing some research on dehydration and incineration process. And this is not a hamburger on the grill. Of course you know that because you saw lots of pictures yesterday. But that, that brings to mind a lot of the barriers we have in trying to get some of this research done. It's not high on the list. It's really has a small interest. There's not a lot of interest out there. I mean, we in this room might think that it is human waste in the backcountry is the most important issue that faces mankind, but it's really not. And there's a lot of taboo related to it. And it's not pleasant research. And I expect as Geoff is dehydrating and incinerating horse manure in his lab, the girls aren't exactly lining up outside his lab door wondering what's going on. So we're very, very appreciative of people like Geoff that do research in this area. I just want to say one word about this, which is a refuse incinerator, which we're using to burn the poo after it's dehydrated. There was some mention yesterday about a waste incinerator, and they don't work very well. And I'm sure there's a few different models out there. The one I'm familiar with is the store burn model. Requires a fuel source, and of course, Bees is interested in reducing fossil fuel use. But we kind of like this one because it just requires an electrical source. Okay. It's not actually designed to burn sewage. It's designed to burn refuse. It was created by the US EPA to reduce emissions and to be used in the backcountry to burn garbage. But once we dehydrate the poo, then we can actually use this to burn it.
So I think composting research and the science behind composting is really, really critical to make sure that we follow this approach to life is like a sewer. So if we put into the composter poop and wood chips, I think we should take the precautionary approach to make sure that we're not getting poop and wood chips out the other end and calling it compost. So what that requires is measuring and analysis standards, some protocols that we follow that are uniform, that are replicatable, much like sewage treatment or municipal solid waste composting or the composting of sewage sludge. So a lot of these happen on larger scales, and the science behind them has been well developed. There isn't a ton of publications on smaller scale sewage treatments, such as a septic tank in your home or small composting toilets, partly because the motivation isn't there. And they're also somewhat expensive to run these analyses and tests. So I'll discuss that as well. So there's a number of key controlling variables that it makes sense to monitor, and some of these are being monitored by organizations running composters, but not all of them. So temperature seems to be the one talked about most, and it is important. But if temperature is the only variable measured, then there can be a number of other blocking variables that will make it look like the composting process is complete, even if you had a nice temperature spike, but something's blocking, leaving an unfinished end product. So some of those are moisture, percent soil moisture, and aeration. So now when we're looking at the end product and we're analyzing it for effective composting, we need to look at pathogen reduction, which is simply you take it to a little sample to the lab. You can send it to most labs, and they all are familiar with the process. It needs to be less than 1,000 fecal coliform counts per gram in order to meet Class A compost under the EPA standard. And then something that isn't talked about a ton is stability and maturity of the compost. So stability relates to the carbon degradation, how well decomposed are the carbonaceous molecules and compounds in that mixture of poop and wood chips. And so in order to assess that, you need to get a degree of CO2 evolution, which is how much microbial activity is still going on in your end product. Obviously, if it's finished, there won't be much because the bacteria aren't consuming the product, or oxygen uptake. So conversely, those microbes need oxygen. And maturity relates to the state of the nitrogen in there. So if you have a high degree of ammonia in your compost or in your end product, and you disperse that on your land, or you use it as fertilizer, it's really it's going to rob oxygen from your soil. It's going to be phytotoxic to the plants and the environment around. So you need to make sure that the nitrogen has moved through along the nitrification process from ammonia to nitrite and then to nitrate. In my research on 6 composters in the Canadian Rockies, the nitrification process seems to be blocked. So it goes from ammonia to nitrite reasonably well, but nitrates aren't being developed. I'm not totally sure why, but I'm only in the first year. So the way to analyze this in the lab is to look at ammonia concentration, or ammonium, if it's dissolved in the compost matrix. So obviously these are really challenging. You can't do them out in the field. It's expensive to send them to the lab. What lab are you going to send them to? Challenging for the site operator who built a composter because it was supposed to be easier. So what I'm testing is a small, I actually don't have it here, but if you want to come and see it, come and talk to me. There's a small kit. It comes in a small jar with 2 paddles. It's $10 a test, and it's called the Solvita Compost Assessment Kit, and it's been certified by compost councils in California, United States, and in Europe as a feasible and viable index for relating to stability and maturity. So the 2 paddles have a gel matrix on them, which reacts with the carbon dioxide evolved from the small compost sample and from the ammonia that's evolved. So I haven't, and nobody else has done the calibration with human waste compost, and hopefully I'll have those research results by the end of the year. And the final point on composting, this is well documented in the research, that the carbon to nitrogen ratio isn't a viable indicator of compost completeness for a number of reasons. So the other side of things, I think compost works well where you can dispose of the end product on site, close the loop, recycle the nutrients, but where you can't and you have to fly the compost out anyway, probably doesn't make as much sense. So in those cases, I think urine separation simply on its own is a great solution, and the final step, dehydrating that end product, whether you develop your own system like I did or use one of those dehydrators out there, they look like great options. So some data just came in this morning from a mass balance experiment that I was running in the Bugaboos. So I have a field technician who's collecting data both on door counts and on the change in mass in the barrel underneath a standard toilet, which is all of the excrement goes into one hole, versus solids go into the hole and the urine is diverted away, both with the seat and a urinal, so men don't have to sit down. And I think there'll be a little while before we start doing that. And so the barrel flyout was 0.63 kilograms per use, and a use is 2 door counts. Someone opens the door, closes the door, goes tick for 1, they leave, open, close, tick for 2. So that's the change in mass, the average change in mass. This is about over 200 uses over the last week. It's 0.63. And we did the same thing with the urinal, a urine diversion toilet that I've modified. It's closer to the hut, and that's 0.03 kilograms per use. So definitely a significant savings when you install a urine diversion seat and a urinal. So dehydration and incineration. Finally, I wanted to assess what are the benefits and the costs of each of these steps. So you can install a urinal, you can install a seat, you can install exhaust fan, and then you can start dehydrating. You can add heat or you can reduce the relative humidity. And then you can incinerate. But I wanted to know stepwise what is the impact of these. And I think this is important for when we talk about all the different systems we've developed out there, and there's so many different ones and different modifications, hot air panels and this and that, that we need a scalable and transferable index so that we can compare what is the use and what is the benefit to what we've put into it. Associate those with costs and environmental impacts. And so BEES has started well into that with the life cycle analysis study that was just presented. And I think we can take that further with a little bit of information. So that those key pieces of information are a mass balance, or you need a weigh scale. You need to know what's going in and what's going out. And perhaps some small temperature relative humidity loggers to know what's going out the exhaust fan. And a door counter, obviously you need to know how many people are opening the door. So the life cycle analysis takes that a bit further and puts some quantification to the scalar index that was presented by Karen, which is 1 through 5. So the life cycle analysis is used on the impacts on larger projects, usually not small ones, but I think it'll add great value as this research goes forward. And it relates to what are the values and what are the key objectives in this. And we can create a weighting pattern based on that. So the presentation last night about taking the toilets out of Whitney, I thought was a great example because they placed that value on wilderness higher than the than the value of we just want to be able to manage the waste. We're going to do whatever it takes, whatever engineering it takes to get rid of that. So the value set changed, and I appreciated that. So the environmental, a simple index is the CO2 equivalent emissions. What is the cost of these management practices? And we can track those. There's great information, there's great databases available through federal websites of the cost of flying a helicopter, the cost of trucking it out, the cost and CO2 emissions of sewage treatment, et cetera. And then a human impact, DALY, or the impact on a human life for the CO2 emissions, or for an operator working in a small chamber that's high in ammonia concentrations. And then capital costs as well, put those in. So Karen presented some great information on that. I think we can all take that a bit further. So one example, the barrel flyout, the CO2 equivalent emissions of flying poop from the Bugaboos sort of to Golden. There's some transportation by pump truck as well. It's 70 to 100 CO2 equivalent emissions per toilet use, per 2 door counts. So the equivalent when it's incinerated on site, and my field technician just ran the incinerator and he said it worked reasonably well. We need to have it a little bit drier next time. So this is a full-scale 200-liter barrel that I've modified with an insert to allow air to pass through the barrel, which is similar to Joe Arnold's design. And thanks, Joe, for speaking to me 4 months ago. Tried to get him on the phone to get some feedback on this design, and he really helped out there. So this design is working. It's basically his chamber put inside a regular toilet. So I wanted all of these technologies to be able to be modified inside the regular barrel flyout toilet, because most of us in the parks have barrel flyout toilets already. So why build a whole new one when we can modify? And so that the CO2 equivalent emissions in this incinerated barrel of poop was 40 to 50. So when someone says, well, you're incinerated on site, look at all this emissions that's coming off, it's got to be worse. Well, it's not actually worse. It just happens to be right there, and you can see it as opposed to at the sewage treatment plant.
Yeah, I'm wondering what different aspects of aesthetics you considered, and whether for the incineration, what the smoke output is like, and whether that was considered, or was it more just the aesthetics of handling and being around poop?
So I believe when the researchers were looking at incineration as a emission source, they were looking at the store burn model of incinerating human waste, and their emissions are fairly low. But aesthetics was basically odor and visual impacts.
So would that include helicopter and I mean aspects other than just the poop part of it, or
Yes.
Like, okay, so
Yes.
those kinds of things
Yes.
were part of the aesthetics.
So for the helicopter flyout, I mean you would include the fuel source and the fact that it's flying over a wilderness area, it's just not desirable, and all those things that come into that. Yeah. The report is in full is on the Bees website.
I was just curious how the cost of the carryouts were more expensive. Do you guys charge user fees or anything?
No, it was entirely the cost of the bag, which was estimated at $2.50 a bag, and I would imagine there would be considered a few uses per bag. But the more people, I know that was one of the interesting things that came out of this study, was that the busier the area is, the more expensive carryout becomes.
Did that include final disposal of the bags also, those costs? Or
Well, they can be just put in the regular trash, right?
But you guys weren't disposing of those? Those
Not
were up
in
to the user?
not in any particular waste treatment center, no.
If I understand you correctly, you dried the feces before you incinerated. And just if you looked at some sort of correlation between, I guess, emissions and the extent of drying, like if it's just straight or just raw, if you like, in the bucket versus different degrees of drying. That's the first question. The second is, how did you achieve the drying?
So the first question was, have we correlated different moisture contents with emission loads? And no, haven't done that. This is the first run. My field technician ran it a couple days ago and just emailed me last night. So the first question was, does it work? Can we incinerate a barrel of dry poop? And given first run that it did work. He didn't give me a mass. He was supposed to weigh it before and after, like he's supposed to weigh everything before and after, but field technicians, he's an undergrad doing a great job. So I didn't get that data. So the second question, how did we dehydrate it? So what I wanted to know was, A, can we dehydrate it to 15% moisture content or less? Because that's the critical moisture content for this incinerator to function. And the data that are expressed on the website are the incineration of dry mass, not wet mass. So what I did, because the Bugaboos has hydropower, which I think is something different than most of the other huts in probably the Rockies, but maybe not all that different from most of the huts around the world, especially German Alpine Club or in Switzerland and France, where a lot of them do have a source of renewable power. I wanted to make use of that, and I wanted to move the laboratory up into the mountains as much as possible. So I used a dehumidifier buy from Home Depot. It's a 400-watt dehumidifier. Plugged it in. We insulated the basement chamber. It's a very small rock chamber, about 1 meter squared. We put the barrel in there. We put the dehumidifier in there, and there's an exhaust fan. They're all on 110 volt. And so we dehumidified and we heated. So I did those in 2 steps to be able to isolate what's the more important variable, decreasing or increasing the gap in relative humidity or increasing the temperature. And so we used power to dehumidify. But the next step along the way is, can we get the same moisture results with a solar hot air panel or a solar wall? But the rate of inflow, the rate of mass additions, and thus the rate of moisture additions are going to need to be balanced with how much moisture can we pull off. So there's obviously a scalar relationship there. If you increase one, you need to increase the other.